On the 27th of February 1942, Dr. Reginald Victor Jones sits at a wooden workbench in the basement laboratory of the Telecommunications Research Establishment near Malvern, examining a twisted fragment of metal lattice barely 40 centimetres square. The aluminium framework, recovered 3 days earlier from the Bruneval raid on the French coast, represents the first physical evidence British intelligence has obtained from Germany's Würzburg radar system. Jones rotates the fragment under a magnifying lamp. The welds are precise. The aluminium tubes measure exactly 15 millimetres in diameter, with 1.2 millimetre walls. The spacing between elements holds to within 2 millimetres across the entire section. What captures Jones's attention isn't the quality of German engineering. It's the deliberate asymmetry machined into each mounting bracket, a 3.7-degree offset that shouldn't exist in a symmetrical parabolic reflector. The fragment comes from a 3-metre diameter Würzburg system, captured intact by paratroopers of C Company, 2nd Parachute Battalion. Intelligence assessments predicted German radar operated at wavelengths between 40 and 80 centimetres. The captured equipment operates at 53 centimetres. British chain home stations, with their 10 to 13.5 metre wavelengths, can detect aircraft at 150 kilometres, but cannot provide precise bearing information closer than 1 degree. The Würzburg achieves accuracy of 0.2 degrees in azimuth and elevation. For German flak batteries, this precision transforms radar from a detection system into a fire control instrument. Jones measures the parabolic curve of the reflector remnant using a depth micrometer. The surface deviates from true parabolic geometry by no more than 0.8 millimetres across the entire fragment. German engineers have achieved optical quality tolerances in a 3-metre battlefield antenna designed to rotate at 24 revolutions per minute whilst exposed to North Atlantic weather. The dipole feed assembly, recovered separately, shows equally meticulous construction. The feed horn measures 180 millimetres square, with internal dimensions calculated to within 0.5 millimetres of the theoretical quarter wavelength matching requirement. The coaxial connection uses a precision-threaded coupling with 0.1 millimetre thread pitch. Every component reflects manufacturing standards more appropriate to laboratory instruments than field equipment. But the mounting brackets tell a different story. Each one incorporates that same 3.7-degree offset. Jones calculates the effect on the antenna's radiation pattern. A symmetrical parabolic reflector produces a beam with side lobes 23 decibels below the main lobe intensity. The deliberate offset should raise those side lobes to minus 17 decibels, a 6-fold increase in energy radiated away from the primary target direction. For a detection radar, this represents inefficiency. For a tracking system providing targeting data to anti-aircraft guns, it represents something else entirely. Jones requests all available intelligence photographs of Würzburg installations. Photographic reconnaissance sorties over occupied France have captured 17 distinct sites. Analysts at RAF Medmenham provide enlargements showing antenna positioning. At 14 locations, Würzburg antennas operate in pairs, positioned 180 metres apart. The separation distance varies by no more than 5 metres between installations. At the Domburg site on Walcheren Island, 6 Würzburg units form a hexagonal array with 180 metre spacing between adjacent antennas. The geometry isn't random. Jones measures the angular separation between units, exactly 60 degrees. He calculates the interference pattern created by 2 Würzburg radars operating 180 metres apart at 53 centimetre wavelength. The antenna beams, each with that engineered 3.7-degree offset producing elevated side lobes, create a standing wave pattern in the overlapping coverage zone. Where the side lobes intersect, they generate alternating zones of constructive and destructive interference spaced 8.5 metres apart at a range of 5 kilometres. An aircraft flying through this interference pattern experiences rapid fluctuations in the reflected signal strength. The Würzburg receivers, designed with automatic gain control circuits, interpret these fluctuations as target maneuvering. The tracking servos respond by adjusting antenna pointing direction. The adjustments don't improve tracking. They degrade it according to a predictable mathematical function related to the interference pattern geometry. Jones examines the feed horn assembly under higher magnification. The dipole element sits 132 millimeters from the reflector vertex, precisely 1/4 wavelength at 53 centimeters. German engineers have positioned it within 0.3 millimeters of the theoretical optimum, but the dipole itself shows unusual construction. Standard dipole antennas for this frequency use simple rod elements 250 millimeters long, 8 millimeters in diameter. The Würzburg dipole consists of two cone-shaped elements, each 140 millimeters long, with base diameters of 35 millimeters tapering to 8 millimeter tips. Jones recognizes the geometry from theoretical papers published in German technical journals in 1938. The conical elements broaden the antenna's bandwidth from the typical 8% of a rod dipole to nearly 18%. This allows the Würzburg to operate across a frequency range from 485 to 575 MHz without retuning. The bandwidth exceeds operational requirements. German flak control needs accuracy, not frequency agility. A narrow band design would provide better sensitivity and simpler receiver circuitry. The extra bandwidth makes sense only if German operators intend to shift frequencies rapidly to avoid jamming. But frequency agility conflicts with the fixed interference pattern created by the precise 180-meter antenna spacing. Change the operating frequency by 10 MHz and the interference null's shift position by 0.9 meters at 5 kilometers range. The tracking errors induced by the interference pattern become unpredictable. Jones requests technical analysis of the transmitter section recovered at Bruneval. The power amplifier uses a German-manufactured magnetron producing 8 kilowatts peak power in 2 microsecond pulses at 3,750 pulses per second. The duty cycle yields 60 watts average power. British magnetrons of comparable frequency produce 15 kilowatts peak, 112 watts average. The German tube operates well below the theoretical efficiency limit for magnetron design at this frequency. Engineers at TRE test the captured magnetron on a laboratory power supply. It produces 8.2 kilowatts at 485 MHz, but only 5.9 kilowatts at 575 MHz, a 28% power reduction across the antenna's designed bandwidth. The output power varies inversely with frequency across the entire operating range. The power variation correlates directly with the elevated side lobe design. At 485 MHz, where the magnetron produces maximum power, 18% of radiated energy exits through the antenna side lobes. At 575 MHz, with reduced transmitter power, the main beam intensity drops by 28%, but side lobe radiation decreases by only 19%. The ratio of main beam to side lobe energy degrades from 5.6 to 1 to 4.3 to 1. German engineers have created a radar system that becomes less accurate precisely when operators shift frequency to avoid jamming. RAF Bomber Command operations over the Ruhr Valley between March and July 1942 provide field data. Navigation logs from 487 sorties report encountering predicted German flak concentrations at 17 locations where photographic reconnaissance has identified Würzburg installations. Flak intensity, measured by shell counts within 500 meters of bomber formations, averages 47 rounds per minute at these locations, compared to 29 rounds per minute at sites without radar control. Hit probability increases by a factor of 2.3. But the hit distribution shows anomalous patterns. Damaged aircraft cluster in groups of 3 to 5 flying in close formation. Dispersed aircraft, separated by more than 200 meters, experience hit rates 40% lower than the average for radar-directed flak. Squadron leader Harold Bufton analyses the bombing photographs and track data. Aircraft hit by radar-directed flak show damage concentrated on the port or starboard side, not on top or bottom surfaces. The lateral damage pattern suggests flak shells detonate consistently to one side of the target aircraft. Bufton correlates damage locations with aircraft heading relative to the Würzburg site bearing. Aircraft approaching on headings within 30 degrees of the direct line between paired Würzburg antennas sustained 68% more hits than aircraft approaching from other directions. The correlation holds across all 17 radar-equipped sites. Jones calculates the expected tracking error induced by the interference pattern. An aircraft flying perpendicular to the baseline between paired Würzburg antennas crosses interference nulls every 8.5 meters. At a closing speed of 90 meters per second, typical for a Lancaster at 4,500 meters altitude, the aircraft traverses 11 nulls per second. The Würzburg servo system, with mechanical response time of 0.18 seconds, cannot follow these rapid variations. The tracking solution oscillates around the true aircraft position with an amplitude determined by the interference null spacing and the servo gain. For the standard German servo gain setting of 2.4, Jones predicts a tracking error of plus or minus 22 meters in azimuth at 5 kilometers range. Flak shells detonating 22 meters to one side of the target explain the observed lateral damage pattern. But aircraft approaching parallel to the Würzburg baseline, along the line connecting paired antennas, don't cross interference nulls. They fly along a null, experiencing constant signal strength. The servo system tracks accurately. These aircraft should sustain maximum damage. The operational data shows the opposite. Aircraft on parallel approaches experience 40% fewer hits than aircraft on perpendicular approaches. The discrepancy suggests German flak crews compensate for the lateral tracking error when aircraft approach perpendicular to the baseline, but apply the same compensation when aircraft approach parallel, creating a new error in the opposite direction. Jones examines German flak training documents captured in North Africa. The instruction manual for Würzburg operators includes a correction table listing bearing adjustments for different target approach angles. The corrections range from minus 0.8 degrees to plus 0.8 degrees. They're intended to compensate for systematic tracking errors induced by the antenna side lobe pattern. But the correction values assume single antenna operation. German doctrine calls for using paired Würzburg systems for redundancy and coverage, but the training materials don't address interference between paired units. Flak crews apply single antenna corrections to dual antenna geometry. The corrections, designed to improve accuracy, instead guarantee predictable errors. The systematic nature of the tracking errors originates in German radar development history. Engineers at Telefunken developed the Würzburg design between 1938 and 1940, basing performance specifications on anticipated jamming threats. British chain home stations operating at 10 to 13.5 meters wavelength were vulnerable to simple noise jammers radiating across a broad frequency range. German designers assumed British bombers would carry similar jammers operating at shorter wavelengths. The wide bandwidth design of the Würzburg dipole allows frequency shifting to avoid narrowband jamming. The elevated side lobe pattern, created by the 3.7-degree mounting offset, reduces main beam intensity but preserves enough side lobe energy to maintain tracking even when the main beam frequency is jammed. Telefunken engineers tested prototype Würzburg units individually, measuring tracking accuracy against towed aerial targets at the Rechlin test facility between August and December 1940. The prototypes achieved 0.2-degree accuracy under ideal conditions. Production units, manufactured at 8 facilities across Germany and occupied territories, maintained the same accuracy in acceptance testing. The testing protocol specified single antenna operation. Nobody evaluated paired antenna performance because German doctrine in 1940 didn't yet call for deploying Würzburg systems in pairs. That doctrine emerged in 1941 after British bombing raids demonstrated the need for redundant coverage. By then, 340 Würzburg units had entered service. Retrofit would require redesigning the mounting brackets and dipole feed assembly, an 8-month development program affecting production of 60 units per month. German production priorities in 1941 emphasize quantity over refinement. Luftwaffe Flak Command requests 800 Würzburg units to defend industrial centers in the Ruhr, Hamburg, and Berlin. Telefunken's production capacity, even with subcontractor manufacturing, peaks at 73 units per month. Engineering resources focus on expanding production rather than improving design. The interference problem remains unaddressed. Field commanders, unaware of the systematic tracking errors, attribute accuracy problems to crew training deficiencies. Gunnery schools intensify training using the correction tables derived from single antenna testing. Crews become more proficient at applying corrections that worsen their targeting accuracy. Oberfeldwebel Klaus Richter commands a Würzburg-directed flak battery defending the Blohm and Voss shipyards in Hamburg. His diary, recovered by British intelligence in 1945, documents the frustration of radar-directed air defense. 17th May, 1942. 8 Wellingtons approached from the northwest at 0147 hours. Würzburg No. 1 acquired lead aircraft at 14 kilometers range, tracking stable at 11 kilometers. Passed targeting solution to predictors at 9 kilometers, commenced firing at 7.8 kilometers range, 73 rounds. No hits observed. Aircraft passed overhead at 4.2 kilometers altitude. Bombs impacted 800 meters south of aiming point. Würzburg showed steady track throughout engagement. Post-engagement analysis indicates shells detonated 40 to 60 meters east of bomber stream. Cannot explain systematic error. Same error observed in 3 previous engagements against formations approaching from northwest. Richter's battery operates 2 Würzburg units positioned 180 meters apart on an east-west baseline. Bombers approaching from the northwest cross the baseline at approximately 45 degrees, precisely the geometry that generates maximum tracking error from the interference pattern. Richter's crews apply the standard correction for approach angle, adding 0.4 degrees to the azimuth solution. The correction assumes single antenna operation. With 2 antennas operating, the interference pattern creates a tracking error of -0.6 degrees. The applied correction changes the error from -0.6 degrees to -0.2 degrees. An improvement, but still generating the observed 40 to 60 meter miss distance at 7.8 kilometers range. Richter attributes the accuracy problem to equipment defects and requests replacement Würzburg units. The replacement systems exhibit identical performance. British countermeasures exploit the discovered vulnerability beginning in August 1942. Bomber Command issues tactical guidance directing formation leaders to adjust approach headings to fly perpendicular to the suspected bearing of German radar sites. Navigation aids don't provide sufficient accuracy to guarantee perpendicular approaches, but even approximate alignment increases the tracking error from 22 meters to as much as 45 meters when aircraft enter the interference pattern at optimal angles. Bomber loss rates over Würzburg defended targets decrease from 4.7% in June 1942 to 3.1% in October 1942. The reduction doesn't correlate with changes in German flak density or fighter opposition, only with refined approach geometry. German intelligence recognizes the shift in British tactics by November 1942, but fails to identify the underlying cause. Luftwaffe analysis attributes the changed approach patterns to improved British navigation equipment, allowing more precise target runs. Recommendations focus on increasing flak density around predicted approach corridors rather than investigating radar performance. Würzburg production continues without modification through 1943. By January 1944, 2,847 Würzburg systems defend German and occupied territories. All exhibit the same systematic tracking errors when operated in paired configurations. post-war interrogation of Telefunken engineers reveals the source of the 3.7-degree mounting offset. Dr. Wilhelm Runge, lead designer of the Würzburg antenna, explains that the offset compensates for a mechanical asymmetry in the elevation drive system. The antenna mount uses a single motor driving a large ring gear. The gear backlash, approximately 0.08 degrees, creates pointing errors that vary depending on the direction of antenna movement. By offsetting the feed assembly, Runge introduced an optical bias that counteracts the mechanical backlash when the antenna tracks targets in the most common engagement geometry. Aircraft approaching from the direction of England. The compensation works perfectly for single antenna operation against targets approaching from the west. It creates the elevated side lobe pattern that generates interference nulls when two antennas operate in proximity. Runge never anticipated paired antenna deployment. His design optimized performance for the operational doctrine current in 1939, single long-range detection radars operating independently at sites spaced 20 to 40 kilometers apart. The doctrine changed, but the hardware didn't. The elegant mechanical compensation that improved single antenna accuracy became a systematic vulnerability in the dual antenna configuration that German air defense doctrine adopted in 1941. Dr. Reginald Victor Jones publishes his analysis in a classified report circulated to RAF Bomber Command, the Air Ministry, and Allied intelligence services in April 1943. The report, titled Systematic Errors in German Würzburg Radar Tracking, runs to 127 pages with 43 technical diagrams. It includes specific recommendations for approach headings optimized for each known Würzburg installation, calculated based on photographic reconnaissance data showing antenna spacing and orientation. The recommendations account for site-specific geometry, improving their effectiveness compared to general guidance issued in 1942. American bomber crews receive similar briefings beginning in June 1943, as the 8th Air Force intensifies daylight raids over Germany. The combination of optimized approach geometry and formation tactics reduces radar-directed flak effectiveness by an estimated 38% compared to early 1943 baseline performance. German flak batteries compensate by increasing ammunition expenditure from an average of 4,800 rounds per bomber, downed in January 1943, to 16,000 rounds per bomber downed by March 1944. The increased ammunition consumption strains German logistics. Monthly flak ammunition production, 3.2 million rounds in January 1943, increases to 4.8 million rounds by March 1944, despite competing demands from the Eastern Front. The technical understanding of Würzburg vulnerabilities influences Allied development of radar countermeasures. British scientists design window, strips of aluminium foil cut to half-wavelength dimensions, specifically to exploit the Würzburg's sensitivity to targets smaller than aircraft. A single Lancaster bomber releases 2,000 window bundles, each creating a radar return equivalent to a heavy bomber at Würzburg frequencies. The metallized strips, falling at 0.9 meters per second, create a slowly descending cloud of false targets. Würzburg operators cannot distinguish individual aircraft within the window cloud. The interference pattern that created tracking errors against real aircraft creates complete tracking failure against the mixture of aircraft and chaff. RAF Bomber Command deploys window operationally during the Hamburg raids of the 24th of July, 1943. The 746 bombers participating in the first raid drop 92 million window strips. Würzburg systems attempting to track targets through the chaff cloud report continuous lock breaking and false target acquisition. German flak effectiveness drops to negligible levels. British bombers successfully destroy approximately 45% of Hamburg's industrial capacity over 4 raids between the 24th of July and the 3rd of August. Loss rates average 2.8% compared to 5.4% for comparable raids against Hamburg in June 1943 before window deployment. German engineers attempt to modify Würzburg systems to counter window, adding circuits that discriminate targets based on radial velocity. True aircraft exhibit closing velocities of 80 to 120 meters per second depending on approach angle. Window falls at 0.9 meters per second. The velocity discrimination circuits, deployed beginning in October 1943, restore some tracking capability. But the modifications can't eliminate the fundamental interference problem created by paired antenna operation. British bombers continue exploiting optimal approach geometry whilst deploying window. The combination reduces radar-directed flak effectiveness to roughly 40% of pre-window performance throughout 1944. Dr. Reginald Victor Jones continues as Director of Intelligence at the Air Ministry through the end of the war, providing technical analysis of German weapons systems including V-1 flying bombs and V-2 rockets. His methodical approach to understanding enemy technology through analysis of captured equipment and operational data establishes a template for scientific intelligence work that extends into the Cold War era. After demobilization in 1946, Jones accepts the Jacksonian Professorship of Natural Philosophy at the University of Aberdeen, where he lectures on physics and infrared spectroscopy for 35 years. Jones publishes his wartime experiences in Most Secret War, released in 1978. The memoir details his analysis of German radar systems, including the Würzburg investigation, for a general audience. Technical appendices provide engineering details of the interference pattern calculations and tracking error analysis. The book becomes standard reading for intelligence analysts and military historians studying the role of scientific intelligence in modern warfare. In a 1980 interview with the Imperial War Museum, Jones reflects on the Würzburg analysis. The Germans built a technically excellent radar system and then deployed it in a configuration that guaranteed systematic errors. The errors weren't random failures. They were predictable consequences of interference between paired antennas. What's remarkable is that nobody in the German development chain recognized the problem. They tested individual units thoroughly, but never evaluated the system as actually deployed. We won not because our equipment was superior, but because we understood their equipment better than they did. Jones receives numerous honors for his wartime service, including appointment as Companion of the Order of the Bath in 1946 and elevation to Commander of the British Empire in 1955. He retires from Aberdeen in 1981, but continues writing and lecturing on the history of scientific intelligence. His technical papers on radar theory and countermeasures influence post-war development of air defense systems. Modern phased array radars incorporate design features explicitly intended to avoid the interference problems that plagued the Würzburg system. Element spacing precisely calculated to prevent grating lobes, adaptive algorithms that recognize and compensate for multipath interference, and testing protocols that evaluate system performance in operationally realistic configurations rather than idealized single-unit scenarios. Jones dies on the 17th of December, 1997, at age 86. His personal papers, donated to the Churchill Archives Centre at Churchill College, Cambridge, include the original calculations performed during the February 1942 analysis of the Bruneval raid material. The calculations, written in pencil on graph paper, show the step-by-step derivation of the interference pattern geometry and predicted tracking errors. The mathematical analysis that revealed the systematic vulnerability of Germany's air defense radar remains accessible to historians and engineers studying the technical dimensions of the Second World War. The twisted fragment of Würzburg antenna that Jones examined in February 1942 is preserved in the Royal Air Force Museum at Hendon. Museum conservators maintain it in a climate-controlled case alongside the complete Würzburg system captured at Bruneval. The mounting bracket, with its 3.7-degree offset visible in the machined angle, illustrates how a design optimization intended to improve accuracy instead created a systematic vulnerability when operational doctrine changed. The technical legacy extends beyond the specific failures of German radar deployment. Modern systems engineering emphasizes testing in realistic operational configurations, understanding how individual component optimizations interact when integrated into larger systems, and recognizing that tactical doctrine and technical design must evolve together. The principles Jones applied in understanding enemy technology, methodical analysis of physical evidence, correlation with operational data, and systematic testing of hypotheses, establish standards for technical intelligence work that remain current 8 decades later.